it's still mind-boggling to me that like electromagnetic waves, which is something to do with magnetism, is the same as light. Like,
Right, okay, sorry. I did kind of go through that a bit quickly, didn't I? Sorry, I'm a bit nervous. This is the first time I've ever done a talk outside of an academic conference. So it's a bit different. These are my peers, not like colleagues. So yeah, it is weird, and anybody who says that they understand it is lying. This is the curse of academia. Like, the more you study something, the less you understand it. And I don't really know if this is correct, but the best way that I can think to explain the wave-particle duality is it's always travelling as a wave. And when you look at it, when you observe it, it collapses into a single point, a particle. That's basically Heisenberg's uncertainty principle. You can either know how fast something is going, or you can know exactly where it is. The more confidence you have in one, the less confidence you can have in the other. I see it as basically you're looking at a wave as it's travelling, but the moment you look at it, it just becomes a single point. Because what you're taking a measurement of it at that exact moment. So they're kind of one and the same. All categories are meaningless. This is an abstraction that we came up with before we knew anything about light. Anything else? Yes?
Yeah, the absorption spectra, for example, hydrogen.
Yeah.
You have a specific absorption spectrum. Does it change when it's like in a compound, when you have H2O?
Yes, so all of it's very dependent on the quantum mechanics isn't my thing. Just putting that out there. So sorry if anybody's watching this on YouTube and they're screaming at me because I'm being over simplistic. But essentially there are energies associated with every bond, and there are configurations where electrons can be in that bond. The transitions between them change. So when you look at something, say if you're looking at a no H bond, if you go, say, on the NIST website, you'll look and you'll see that there are so many different wavelengths that are corresponded with that bond, because there are many different transitions that can be there. So we look at the data and then we try and work backwards, essentially, if that makes sense.
I think I have a way to phrase one of my questions.
Okay.
So my basic background in electronics that I had in my bachelor's said that a laser is basically shooting photons at one direction.
Yeah.
However, if Wacht, I'm not sure if he's here, but every single time when Wacht is talking about Wi-Fi and stuff like that, and like having a Wi-Fi connection from Ghent to Antwerp, then the information that's encoded, like, is not transferred in a straight line, but is transferred in like a bubble, basically. And so they don't have to have, they not only have to have like a line of sight at the exact same point, but there also has to be enough room below and enough room above in order to actually transfer.
Yeah, because we can't say where any given photon is at any given time. We can describe the system as a whole, because think of it like a probability distribution. It's likely to be in this region, but admittedly I don't know an awful lot about Wi-Fi, but I would imagine that's why data gets lost sometimes, because photons don't always behave how you tell them to. That's just part of life. I don't actually know how significant that is with Wi-Fi, but given my understanding, yeah, probably. It would explain why it struggles getting around things.
Yeah, but then how can't you just create like a satellite that does the same thing as a laser, just shooting the photons in a straight line, or is it because the wavelengths are bigger, or?
We certainly try. That's how generally directional signaling works. You can point it and you know lots of properties about the wave. You know how it's going to travel through the medium that it's travelling through. You can do your best guess, and I think that's what people try and do, but honestly, this is not my area of expertise. I'm mostly doing this so you can get an appreciation for how astronomers do things, because I'm going to jump into cosmology next, and everything is based on spectroscopy. Everything we know is based on spectroscopy. Christoph?
You said the next slide.
Yeah.
You said at the beginning of this graph is like a fingerprint of something?
Well, so all of these here, these are what I would call like a chemical fingerprint. They correspond to a particular energy transition.
How do you take in consideration noise? I mean,
Statistical analysis. If you want to look at the code, I'm happy to share it with you. Unless people don't mind me talking about statistics for a little bit. Does anybody mind? Okay. So we do something called a Gaussian approximation. Each one of these was modelled with a single Gaussian. I went through, I isolated very small regions. I did a Gaussian peak for each one of them with a little function that I made myself to do the thing. And you basically see where the peak is on the Gaussian. You can read off what the wavelength is, and then you can look in the database and figure out what does that correspond to. Does that make sense?
How big are the data sets that you're working with?
The ones that I'm working with here, this is very small. It's maybe a couple of gigabytes. You can download the whole of a typical data release from the SCSS, and I think it's around about 2 terabytes for each one. It's not a lot because it's very simple numerical data. It's just points on a graph, essentially. This is an abstraction. This is a major abstraction from what we actually have.
Does this mean that magnesium 2 and He1 might actually be C3 and Fe3?
Not likely. So each one of these, like the extent, talks about intensity, so the amount that is there. We know, because we know an awful lot about galaxies and what they're made up of, whether things are being likely. So with the way that this data is normalized, it's binned and rebinned and shown off and averaged and all of that. And this lines up pretty perfectly, like less than 5% variation for each thing that I've identified. And they are all things that we would expect to see. The only questionable part is the neon. But I spoke to my tutor about it at the time, and he was like, it's perfectly reasonable. They suggested in the bigger paper that they saw some